Hello friends, welcome to the session. Continuation of chapter 4 inverters, that is classroom workbook questions. In the last session I discussed up to question number 7, that all of you see the classroom workbook. Yes, up to question number 7 it is completed. Then go through with question number 8. First read the question. Yes, all of you start. Take the classroom workbook. Open chapter 4 inverters. This topics VSI and CSI, that is single phase bridge inverters. Okay. A single phase full bridge inverter is fed from a DC source such that fundamental component of output voltage is 230 volts. Find the RMS value of thyristor and diode current for the following loads. Under that, question number A is for R equal 2 ohms. B is if R equal 2 ohms, XL equal to 8 ohms, XC equal to 6 ohms. That you want to calculate. Okay. Given is, see what is the solution of this problem. Okay. Given is single phase full bridge inverter. RMS value of fundamental output voltage is 230 volts. This RMS value of fundamental output voltage. That under that first one is for R load. R equal to what it is given? For R load of R equal to 2 ohms. Okay. The first one, you calculate RMS value of thyristor and diode currents for a resistance of 2 ohms. Then you tell me what is the fundamental output current, you tell me. I01 equal to V01 by R. That is 230 by, that you calculate, 230 by 2. How much you get? 115 amperes. Okay. Then you calculate RMS value of thyristor current and diode currents. Okay. You calculate RMS value of thyristor and diode currents. Then for purely resistive load means, if you draw the waveforms, you know that this is V0 waveform. That this is fundamental output voltage. This is V01. We know that this is for R load. Na? Resistive load means voltage and current waveforms are same. This is pi, this is 2 pi. Then I want to draw the fundamental current. This is V01 and this also I01. Okay. Then if you draw with respect to each thyristor, each switch or each thyristor, let I am IT1, IT2. That here T1, T2 is conducting. This is T3, T4 is conducting. With respect to each thyristor means, we get the current like this. This is the fundamental current. But here T3, T4 is conducting. That's why 0. Then you draw the, with respect to each diode. This I am drawing the waveforms for purely resistive load. With respect to each diode means, we know that for purely resistive load, the feedback diodes cannot work. That concept you know. That's why. What the current supplied by the feedback diodes? 0. It cannot work. Okay. Here, this is Im. Okay. This Im equal to root 2 I01. This you take. Understood? Now from this you want to define what is the RMS value of each thyristor current and RMS value of each diode current for resistive load. Okay. Can you tell me what is the RMS value of each thyristor current? Yes. RMS value of each thyristor current is ITR equal to, it's just like half wave rectifier output na. Then how to write? 1 by 2 pi integral 0 to pi Im sin omega t d omega t. Yes. Can you define like this? Clear? Then 1 by 2 pi integral 0 to pi. What is Im? Root 2 into. What is I01? This 115. Sin omega t d omega t. Then integrate and substitute the limits. We can get, RMS thyristor current na, Im square sin square omega t d omega t whole to the power of 1 by 2. Yes. This is square na, sin square omega whole to the power of 1 by 2. Then integrate and substitute the limits. We can get the RMS thyristor current equal to, we can get the value of RMS thyristor current equal to, we can get directly this equal to Im by 2 na, half wave rectifier output Im by 2. This half wave rectifier output na, Im by 2. Then what is Im? Root 2 into 115 by 2. Then this we can get 81.33 amperes. This is the RMS thyristor. Directly also you can write because it is a half wave rectifier output. Yes, RMS thyristor current equal to, you can write Im by 2 directly, 81.33 amperes. Next, what is the RMS diode current? RMS diode current equal to 0 amperes because for R load, feedback diodes cannot work. For R load, feedback diodes cannot work. Feedback diodes, okay, cannot work. Okay. This is question number A. Under 8th question, this is question number A. That you will see question number B. Yes, but it is given. Concentrate on question number B. For R load, for RLC load it is given na, R equal to 2 ohms. XL equal to how much? Given is 8 ohms. XC equal to 6 ohms. Then XL greater than XC. This is lagging or leading? Lagging loads. Lagging loads. XL greater than XC na, this is lagging power factor loads. Okay. Then what is pi? Tan inverse. XL minus XC. 8 minus 6 by 2. How much? 45 degrees you can get. Okay. Then you calculate average thyristor current, RMS thyristor current and RMS load current here. How much you can get? RMS thyristor current and RMS load current. Okay. Yes. What is Z1? Z1 equal to square root of R square minus R square plus XL minus XC whole square. This Z1, how much you can get? That you simplify. This we can get Z1 equal to first this is Z1. Then what is I01? I01 equal to V1 by that is V1 by Z1. What is V1? RMS value of fundamental output voltage. This is how much it is given. This V01 by Z1 230 by square root of R square S 2 square plus 8 minus 6 whole square. This we can get. RMS value of fundamental current we can get 81.317 amperes. 81.317 amperes. Okay. Now, if you draw the waveforms in this case, now tell me. This is for RLC, XL greater than XC. This I am drawing in one cycle. Okay. Then you draw the current waveform. This is I01. Yes, it's a lagging load. Yes. This how much angle? This is 45 degrees. This also how much angle? This also 45 degrees. Lagging angle. Okay. Then if you draw the with respect to each thyristor. Yes. With respect to each thyristor. For example, you take IT1, IT2. Here T1, T2 is conducting. Here T3, T4 is conducting. We know for lagging loads means first to diode, next to switch. Na? This is D1, D2. This is T1, T2. D3, D4. T3, T4. Then what is the current waveform? Here T1, T2 is conducting. This is pi. Remaining, there is no conduction of T1, T2. I am talking about with respect to T1, T2. Okay, this is T1, T2. If you draw the D1, D2 current waveform with respect to diodes, D1, D2. Okay, this is D1, D2 conduction. This is pi. This is 2 pi. In one cycle. Okay. This is which device is conducting? D1, D2. It's clear? Tell. This total is 180 degrees. This is 45 degrees. Then this is how much? 135 degrees. Then you want to find RMS value of thyristor current and diode current. Na? Now you calculate what is the RMS value of thyristor current. How many pulses per cycle? Total is 1 pulse. Na? This is 2 pi. Total is 1 pulse. Then time period is 1 by 2 pi. Integral 0 to how much angle it is conducting? 135 degrees. 135 degrees means 3 by 4. 0 to 3 by 4. Then Im. That Im is written as root 2 I01. That is root 2 into I01. 81.317 sine omega t. How much angle? This is 45 degrees minus 45 degrees whole square d omega t whole to the power of 1 by 2. Very simple. One pulse time period is 2 pi. How much angle it is conducting? 135 degrees. 0 to 3 by 4. 3 pi by 4. Im sin omega t whole square. Im means root 2 into I naught 1 whole square d omega t whole to the power of 1 by 2. Then you do this one. Simplify. We can get the RMS value of thyristor current equal to 54.818 amperes. By simplifying this we can get 54.818 amperes. That you do. Okay. Can you write what is the RMS value of diode current? Simple. Here also how many pulse for diode? One pulse. 1 by 2 pi into 0 to pi by 4. That is Im sin square omega t minus 45 d omega t. Im square sin square whole to the power of 1 by 2. That Im you know, Im is root 2 I naught 1. Finally you substitute. Then you can calculate by substituting the limits. We can get 17.328 amperes. Okay, this about what exactly diode currents and thyristor currents for different loads. Sorry, for resistive load and RLC load. This is RMS value of thyristor current, RMS value of diode current. This is RMS value of thyristor current and RMS value of diode current. Okay, this is 1 by 2 pi into 0 3 2 pi root 2 81.3 sin omega t minus 45 whole square. Okay, then d omega t whole to the power of 1 by 2 whole to the power of 1 by 2. That you remember. Okay, clear? Understand? This note. This is question number 8 under A, B question. Quick, note down. Then go through with question number 9. Yes, concentrate. 9th question, all of you. What is the solution for this question? A single phase full bridge inverter has RLC load R equal to 4 ohms, L equal to 35 millihenry, C equal to 155 microfarads. The DC input voltage is 230 volts and the output frequency is 50 Hz. Find the first question is find expression for load current up to fifth harmonic. Also calculate RMS value of fundamental load current, the power absorbed by the load and the fundamental power, the RMS and peak currents of each thyristor, the conduction time of thyristors and diodes if only fundamental component is considered. Okay. Given is single phase full bridge inverter. Single phase full bridge inverter. Okay. RLC load R equal to 4 ohms, L equal to 35 millihenry, then C equal to 155 microfarads. This is given data. Supply voltage is 230 volts. Frequency is 50 Hz. Okay. And that first one is find the expression for load current up to fifth harmonic. up to fifth harmonic. First I am writing expression for voltage. Then V naught equal to 4 Vs by pi plus 4 Vs by pi sin omega t. That is up to fifth harmonic you are writing. 4 Vs by pi sin omega t plus 4 Vs by 3 pi sin 3 omega t plus 4 Vs by 5 pi sin 5 omega t. This you know. Now you substitute supply voltage. How much supply voltage it is given? That supply voltage is 230 volts is given. Then by substituting that, then we can get, by simplifying this directly I am writing, we get 292.85 sin omega t plus 97.62 sin 3 omega t plus this 58.57 sin 5 omega t. This is up to this we are getting, this is output voltage. But the question is asked not output voltage. You want to write the expression for output current. Okay. Then you tell how to write Zn equal to R plus n into omega L minus 1 by n into omega C. Then by simplifying this we can get Zn expression equal to, this is 4 plus R plus J. Then 4 plus J into this we can get 11n minus 20.54 by n. By substituting all these values we can get this is Zn. Similarly, how to write theta n? Theta n equal to tan inverse n into omega L minus 1 by n into omega C by R. Then by simplifying this we can get theta n equal to tan inverse. This is 11n minus 20.54 by n by resistance. How much resistance it is given? That 4 ohms. This is generalized formulas. This is Zn and this is theta n. Once you know the Zn and theta n, then I want to calculate Z1, then I want to calculate Z3, then I want to calculate Z5. Then we can get Z1 equal to, by simplifying this, how much Z1 you can get? Square root of 4 square plus, okay, this n equal to 1, 11 minus 20.54 whole square. What is the Z3 you can get? 4 square plus n equal to 3 na, 11 into 3 minus 20.54 by 3 whole square. How to get Z5? Square root of 4 square plus 11 into 5 minus 20.54 by 5 whole square. This is Z1, Z3, Z5. Then by substituting all these we can get directly I am writing this, you simplify 10.345 ohms. We can get 26.46 ohms. Then we get 51.05 ohms. Similarly, what is theta 1? What is theta 2? What is theta 3? You can get. This you substitute n equal to 1, n equal to 3, n equal to 5. By substituting n equal to 3, n equal to 1, n equal to 3 and n equal to 5, then you can get minus 67.25 degrees. This we can get 81.3. This we get 85.5. Then what is the instantaneous output current up to fifth order harmonic? This we get 292.85. 292.85. But the corresponding impedance 10.345 sin of omega t. This minus we are getting now, minus into minus plus 67.25 plus. Yes. Similarly, you want to write the expression for I3 97.62. 97.62. What is the corresponding impedance? Z3 na 26.46 sin omega t, that is sin 3 omega t na, sin 3 omega t minus 81.3 plus. What is the corresponding voltage? 58.57. 58.57 by, what is the impedance? Z5 51.05 sin 5 omega t minus 85.5 degrees. This is the expression for current. By simplifying this, we can get this directly. I am writing 28.31 sin omega t plus 67.25 plus, you get 3.689. 3.68. This simplification, just division only that you do. 3.689 sin 3 omega t minus 81.3 plus 1.1473 sin 5 omega t minus 85.5. This is the first question answer. This is expression for output current up to fifth harmonic. Expression for output current up to fifth harmonic. That is question number A. Clear? Yes. This is question number B. RMS value of fundamental load current. RMS value of fundamental load current. I01. That equal to Im1 by root 2. What is Im1? Only fundamental. This is fundamental component. Na? This is a fundamental third harmonic, fifth harmonic. Fundamental current means that is 28.31 by root 2. Then how much you can get? 20.02 amperes. That you do. That is a question number B. C. Then what is the question number C? The power absorbed by the load and the fundamental power. That means you want to calculate load power and the fundamental power. If you want to calculate load power and fundamental power means first you calculate RMS load current. What is the RMS load current, you tell me? I not RMS. RMS load current. Right. For this type of current waveform, how to calculate RMS load current? That you know, 28.31 by root 2 whole square plus 3.689 by root 2 whole square plus 1.1473 by root 2 whole square. This is RMS load current. By simplifying this, we can get the RMS load current equal to 20.207 amperes. Then once you know this one, then what is the output power? P naught equal to I naught RMS square into R. Then we can get the output load power equal to 1633.3 watts. Then you also calculate fundamental output power, I naught 1 square into R. You know the RMS fundamental load current, resistance you know, that you substitute. We can get a fundamental output power equal to 1603.2 watts. That is question number C. Yes, clear? The same question number 9, concentrate question number D. What it is asked? The RMS and P currents for each thyristor. What is the RMS current of each thyristor? It's a lagging loads that I already explained. RMS current of each thyristor. What is the RMS current of each thyristor? RMS current of each, with respect to each thyristor, it is which output? What the RMS value of each thyristor current means? Then this is RLC load na. with respect to each thyristor means it is a half wave rectifier output. It is a half wave rectifier output means how much you can get? Im by 2. What is Im? Root 2 into, that is Im by 2 means root 2 into IRMS. Root 2 into 20.207 by 2. This is how much you can get. The RMS value of each thyristor current you can get. This is how much? That is 14.286 amperes. 14.286 amperes. What is the peak value of each thyristor current? The peak current is nothing but a maximum current of load current only. This is Im. This is root 2 into 20.207. This how much you can get? Peak current 28.572 amperes. Okay, this is question number D. Then what about question number E? By considering the fundamental component, the conduction time of thyristor and diodes that you want to calculate. Okay, if you consider only fundamental component, this is the fundamental component. What is the diode conduction angle? Diode conduction angle. Diode conduction angle. Diode conduction angle. How much? 67.25 degrees. You want to calculate which one? Conduction time. Then what is the time? Conduction time of diode. Conduction time of diode. Okay. How to get time? That I told so many times. Conduction time of diode. Conduction time of diode equal to theta by omega. That is 67.25 by omega 314. But it is given is degrees. You multiply with pi by 180. This you can get. Then how much you can get? The conduction time of diode is how much you can get? That is 3.738 milliseconds. Then we calculate thyristor conduction angle. What is the thyristor conduction angle? Thyristor conduction angle equal to, we know that in 1/2 cycle 180 minus 67.25. This how much you can get? 112.75. This is degrees. Then what is the thyristor conduction time? Then conduction time equal to thyristor conduction time. How much you get? That is 112.75 by 314 into pi by 180. Then this how much you can get? That you simplify 6.267 milliseconds. These are the question number E. These models recovered. This totally question number 9 is completed. That you concentrate. Quick, no doubt. Asked. In a single phase voltage source bridge inverter, load current I0 equal to, what the load current it is given? 200 sin omega t minus 45. 200 sin omega t minus 45. The DC supply voltage Vs is 220 volts. Okay. What is the power drawn from the supply? What is the power drawn from the supply means power delivered by the supply. That is power drawn from the supply or power delivered by the supply. S. How much? Vs into Is. Then you want to calculate Is. S. This you can calculate average source current. Na? How much angle diodes are conducting? 45 degrees. See, you want to calculate source current that I told in a full bridge inverter. Source current waveform you see. Source current waveform. With respect to source current means how many pulses we are getting? 2 pulses. That's why 1 by pi integral 0 to pi. This is 200 sin omega t minus 45 d omega t. Integrate and substitute the limits. We can get 90 milliamperes. Clear? 200 sin omega t minus 45 d omega t. That you can get 1 by pi integral 0 to pi 200 sin omega t minus 45. This current we are integrating and substituting the limits. Okay. This is what we are getting. This is 200 sin omega t minus 45 milliamperes. That's why we are getting 90 milliamperes. Okay. With respect to, that is full wave rectifier output na, with respect to source current. Full wave rectifier output means what is the average source current of full wave rectifier? That is 2 Im by pi. That we can 90 milliamperes we can get. This is given in terms of milliamperes. Then what is the power delivered by the supply? Power delivered by the supply. That is Vs into Is. Vs is how much? 200. Is is how much? 90 milliamperes. That is 90 into 10 to the power of minus 3. Then how much you can get? Yes. How much? This is not 200. This is 220. This 19.8 watts. Then answer for this one is option and B is correct. This about different models of questions based on this concept. With this, the concept of single phase bridge inverters. Single phase bridge inverters in the sense, mainly I discussed voltage source inverters. But every time no need to tell it is a voltage source inverter or current source inverter. If input is voltage source, then it is a voltage source. If the input is current source, then it is a current source inverter. Here are all the concepts I discussed based on the voltage source inverter, single phase bridge voltage source inverter. Okay. Then I solve so many models. Concentrate on these models, then you can solve any question based on this concept in any competitive exam. That mainly concentrate. Okay. Some lengthy problems also I given, but don't think like this. In GATE exam, this much of lengthy problems it is asking. But I given so many problems in the same problem. I given A, B, C, D like that. In that only one question or two questions we can expect. It is not the meaning all the questions will be asked in the same problem. Okay. But different models I am covering. That's why I given some lengthy problems also. Okay. But don't think like this. That much of length. Not that much of lengthy. In that maybe question A is expect, question B is expect, question C is expect. Like that we can expect. Understood? Okay. With this, the classroom workbook based on this topic is completed. In the next session, we will continue with the next concept in the inverters itself. Okay. Thank you. Concentrate on this.